Okay, so hello everyone. We'll start with the first lecture of the day, which will be lecture 2 by Professor Douglas Durian. And he'll be continuing his lecture from the yesterday's talk, which will be on the physics of wet forms. Over to you, sir.
All right, thank you very much. Oh, could you turn the volume down a little bit? Yeah, so I can raise my voice. It helps me to, if I can speak loudly without, it would be great. All right, good. So thank you. A little lower maybe? All right, good, thank you. So welcome to my second lecture on the physics of foam. So today we're going to move away from these mathematically ideal dry foams to real foams which are wet. And I'll give you sort of a broad introduction to wetness and why thinking about the effects of wetness is important in many contexts, but I'll steer the discussion towards some recent research that I'm doing along with collaborators in Europe, funded jointly by NASA for me and the European Space Agency for them, on the coarsening of wet foams in microgravity aboard the International Space Station. So in fact, our experiments are on board the ISS right now, okay? And they've been there for a few years. So we've got some cool data I'm going to show you, and I want to steer things towards that and how we can understand the results. All right, so just to remind you, there's the movie of a two-dimensional foam that's squashed between plates, and eventually when we want to move to three-dimensional foams, which are wet, okay? So somewhere down here, sort of, right? Where the bubbles have more spherical shapes than polyhedral. And one of the themes, I'll just give away the punchline a little bit. The old way of thinking about it, this process, the effect of wetness on the coarsening process, is the plateau borders, these sticks. They get thicker and thicker as you go down, it gets wetter and wetter. The old thinking is that those simply block the transport of gas between neighboring bubbles, and that's called border blocking, okay? So we'll talk about how that works and what its predictions are and why it actually fails, and how a better way to think about it is to account for the transport of gas across the plateau border, something I call border crossing. And this will give us in the end a way to understand effective coarsening exponents. Okay, I don't believe the growth is truly power law, but there's a way to think about the exponents I want to share with you, and it's a good way to summarize the data. All right, so before we launch in then, let me thank you for all your great questions yesterday and encourage you to keep them coming. All right, so let's see if I can get the clicker to do its thing. Now the computer's over there. Okay, good. So here's a little bit of a review from yesterday. So there's a hierarchy of structure that we talked about, ranging from the molecular to the soap film to the bubble scale to the macroscopic. So there's a hierarchy of structure, and there's lots of things going on at all these scales. Well, today I want to focus on plateau borders, which actually are between the soap films and the bubbles. Okay, so there's an intermediate length scale. And in fact, that's what we see here in this picture. We're looking at the plateau borders, and they're inflated with liquid. They're not lines, okay? They got some structure, and they got some thickness. And in fact, their thickness is much bigger than the film thickness, and their thickness is much smaller than the bubble size, right? So it lives in between these two length scales. So we've got a new length scale in town to contend with, the thickness of the plateau borders, okay? And that's what we'll talk about when we talk about wetness. Please advance. Okay, good. So, so why wetness? So in fact, I think I kind of mentioned it, but really what you're looking at here and what you're seeing the difference between top and bottom is the effect of wetness. Basically, when you look at this picture, you can't tell, I can't tell what the stuff is made of. This structure is independent of the surfactant, the chemical system I choose. It's independent of chemistry. It's also scale independent. You can't look at this and tell me what the size of the bubbles are. What you can see is wetness. So the wetness is the thing that you see most readily, fact, I was talking with Ranjini the other day, and she said she got so good at, she was mixing up foam. Well, I don't know if you know, Ranjini was a postdoc in my lab at UCLA a long time ago. And that was great. She was mixing up foams, and she got really good. She could eyeball the liquid fraction. She was very proud of her skill at just nailing the liquid fraction by looking at the foams. Okay, and that's what you see. You see the wetness. Okay, so that's a key thing to understand. Then is the wetness, and as I said a few times, when it's dry, it's polyhedral. When it's wet, the bubbles are spherical, and the wetness controls the bubble shapes in between. So bubble shapes are important. It's what we see. It affects behaviors, and it's controlled by wetness. Okay. And when we change the wetness, really we're just changing the thickness of the plateau borders until you get so close to unjamming that you no longer recognize the presence of the three topological features, right? The films, the borders, and the vertices. You just don't see them. Really, you just see sort of kissing spheres or spheres that are slightly smashed together, okay? So the plateau borders kind of go away down here, but throughout here, when it gets up, even to being quite wet, you can think about plateau borders and their thicknesses. What I should say is that the wetness inflates the plateau borders, but not the films. The film thickness is really set by the physical chemistry of the surface forces, the DLVO, the double layer repulsion, the van der Waals attraction that's thinning them down. It's the balance of those two things that sets the film thickness. The film thickness is constant going from top to bottom. These spheres are pushed together, but their separation is still the same as the thickness of these films up here. I mean, the stiffness of the potential is not infinite. You can change it a little bit, but primarily it really doesn't change much.
Yeah, so although the film thickness isn't affected, I guess if you look at a film, how far out you have to go before you sense curvature, you see I need my hand.
I know what you mean.
Yeah.
So the film flares into a plateau border.
And that depends on wetness, presumably.
That depends on wetness. Yeah. So here's the film. It's got some small thickness L, and this will flare into a plateau border on each side.
Right, right. Okay. And I guess when that starts depends on...
there's some
kind of radius, yeah. And that depends on wetness and stuff.
That depends on wetness, and we'll tell you all about how that works. So, very important. It's a new length scale in the problem. Very important. All right. Oh, yeah.
Close to the plateau borders, you see those sort of lines that are parallel to the plateau borders, kind of translucent lines.
Yeah.
Yeah, those are.
Yeah. So this is an optical effect. Yeah, it doesn't really reflect any structure. What you're seeing actually is a little bit of light from the soap films. Like, the soap films themselves hit the walls almost perpendicular, okay? And there's another plateau border behind. So here's a plateau border in the bulk. Here's a plateau border on the surface. And this little thing here is the film that's sort of shimmering. So that's the film. Thanks. All right. So the ideal dry limit, way up there. The unjamming limit, so-called point J. I don't know. Andrew, are you going to talk about point J? Okay. Okay, point J is Andrea's baby, okay? It's the unjamming point down here, okay? So she and Sid Nagel named it point J and talk about how it controls behavior. So fine, I discovered it, but I didn't name it point J. So that's down here when the bubbles are spheres. All right, so how thick are those plateau borders? Here's the answer. It's set by the radius of the bubble and the square root of the liquid fraction. Okay, the liquid volume fraction. So how does that work? Okay, well, so here's a picture then that illustrates those three length scales, the film thickness, which is small, the bubble radius, which is the largest, and the plateau border radius of curvature or thickness, little r, is in between. Okay, so there's a picture. So what we're going to do is we're just going to count. We're going to add up the volume of the 3 structural elements. How much liquid volume is in a film? How much liquid volume is in a border? How much liquid volume is in a vertex? And divide that by the bubble volume, and that'll give us an estimate for the liquid fraction. And that's where this equation comes from. So here's how that works. Okay, so liquid fraction is the total volume of liquid divided in a cell, around a cell, divided by the cell volume. And this term represents the volume in a film. So film thickness times film area. It's got a cell scale like LR squared. Okay, so that's easy. How about in the plateau border? Well, the plateau border has thickness R, and it's coming in and out of the page of a distance capital R, the bubble size, right? The plateau borders have the same, their length is the same scale as the bubbles. So we multiply that by R. So the volume of liquid in a plateau border has to scale like this. And the volume of liquid in a vertex has to scale like little r cubed. So those are the 3 terms. Now, only one of these is important, this middle one. The film is so small we can neglect this. And the plateau border thickness is small compared to the bubble radius, so we can neglect r cubed, little r cubed. So this is the only term that we care about. And there you go. There's an estimation of the liquid fraction in a wet-ish foam. Liquid fraction is plateau border thickness divided by bubble size squared. This relation right here. Okay. So Ranjini calibrated herself to this equation, in effect, looking at this picture. All right, good. So here's a topic that's not for today. Since plateau borders change their thickness with liquid fraction, it also affects how fast the foams drain. So drainage is a very important mechanism for the evolution of foams on Earth. It's super, super important. The faster it drains, the faster it coarsens, and the more close you bring bubbles together and they can coalesce. Lots of things happen with drainage. Drainage is very, very important to understand, and there's lots of cool physics in this process. And basically, here's how it works, without giving a big lecture on it. So if you focus in on a little chunk of fluid, you can ask what forces act upon it, and there's 3. Gravity's pulling it down, and there's 2 forces that are kind of pulling it up. If it's flowing downwards, there's a viscous drag that goes upwards, and usually it's wetter below and drier up top, so there's a capillary force that's pulling it up. And we can estimate how much energy per time is being dissipated in the case of capillarity and gravity by a force times the speed, and with viscous drag in terms of viscosity times strain rate squared times the volume over which the shear flow is happening. So I didn't want to actually talk about this in as much detail as I have already. Anyway, the idea is then we want to make sure that all energy is accounted for. So the total sum, I can advance my slides, of power must be 0. So we just basically add up these terms, set them to 0, and substitute in this equation from last slide for the size of the plateau borders, and we get an equation for the speed of the drainage as a function of liquid content. And what goes into it then is a length scale. It's a capillary length, gravitational capillary length. It's a capillary rise length, in fact, it's set by the bubble size, and the critical volume fraction. And there's a it depends on where is the flow. Okay, so shear in the plateau borders, you get that if you have mobile films, so that the flow you get this term if the surfactants are kind of rigid and provide a no-slip boundary condition for the flow. So there's channel flow in the plateau borders. And this dominates dissipation. You get this term if the films are very mobile, so that you get essentially plug flow in the plateau borders, and you get shear flow only in the vertices. So take this equation, supplement it with a continuity equation, you've got yourself a nice partial differential equation that you can use to describe how the volume fraction evolves as a function of space and time in the foam while drainage is happening. And you can also supplement it with things like the coarsening to account for lots of things. So there's lots of cool physics. We could go down this road, but we're not. Here's another road that deals with wetness that we're not going to take. Advance the slides. Please go. Is jamming and unjamming. So, so here is the bubble model for the for the rheology of foams. There should be a movie. Well, whatever. Anyway, what you do is you just suppose that the bubbles are harmonically repulsive if they overlap, and you can easily control the volume fraction or the area fraction in 2D of the system and then perturb away from the wet limit. The idea is this bubble model, so-called, is supposed to capture the behavior at point J. And therefore, hopefully, as we expand away from point J, it also captures the behavior. And there's a number of nice power law relations that control that. This is basically, these exponents are now understood thanks to the work that Andrea and her group have done in collaboration with Sid Nagel. This one is pretty universal for the contact number, and these other ones depend on the potential. So if you have solid, squishy rubber particles with Hertzian contacts, you get different exponents than you get for bubbles. And there's lots of things. Okay, good. Question. Yeah, I ignore the, when we count this in the bubble model, we ignore the overlaps. So in fact, in the bubble model, I can make a volume fraction that's over 1. Okay, but the idea is that close to jamming, the bubbles would deform their shapes. So it would give you a pretty good approximation. And these people in particular, Dave Morse and Tom Whitten, and later Reinhard Holler and Dennis Weir, have worked hard to model the actual microstructure of contact between bubbles and explore how accurate is the harmonic approximation. And that accounts for bubble shapes and the effects that you're mentioning right there, exactly. What they don't mention that's also important is that the interaction is not necessarily pairwise additive. So yeah, so there's lots of cool physics that goes into this, and this would be an interesting road to take, but we're not going to take it today. Yeah, so phi c is the critical volume fraction where the bubbles are just touching, so that overlap is 0. There's no overlap, they're just barely in contact. If you like, it's the point where it's the same structure as you get for absolutely perfectly hard spheres or circles. Okay, so we're going to work on coarsening, and here's some facts about wet foams as background. So here's an important theorem that Dennis Weir proved along with Frederick Bolton, 1991. So take a look at these pictures. They're actually the same structure except for a little bit of paint. You painted or decorated on a little bit of wetness in those plateau borders. And here's a blow up of one of those regions. So here is a film of 0 thickness. And it splits up into plateau border. So there's liquid inside and there's gas out here. So this is a gas-liquid interface. And underneath it is the perfectly dry foam structure. And here's the curvature of those plateau borders. So if you want to make it wetter, you just increase this. And you can think about the force balance at this junction point. You can think about pressures as you march around circles and making sure they add up to 0 as long as you march in a circuit, and prove this decoration theorem. So it's a nice thing. You can paint it on, and the films and things, they won't jostle around, they won't change. It's exactly the same structure. It's perfectly the same, except for a little bit of paint on those junctions. But there's a little bit of a problem. You can only paint on so much. If I make it thicker and thicker, these painted regions begin to merge. Can I find a film that's small? Like here's a small bubble that's shrinking. If you look at this film right here, those painted regions are getting close together. Eventually, they'll merge, and then the decoration theorem fails. So you can only do this for a little bit of wetness. Sriram.
Yeah, no. So you're saying the theorem is that if you have a reference dry form, then if you know the amount of liquid, you can house that amount of liquid in these equilateral circular triangles. Is that
That's correct.
I see. Okay.
That's correct. So this so-called deck. Okay, Rajesh, please.
For the shear modulus, the one that you had in
Going
the,
back a page, yeah.
in the previous slide. So when I think of these bubbles sliding past each other, is this to be thought of as a frictional interaction, or is there zero friction? How do I think of these systems?
Yes. So in the previous slide, I gave you the static shear modulus. And of course, if you shear it at non-zero rate, there will be dissipation. Even at quasi-statically, there will be dissipation because you will knock bubbles past each other. They'll rearrange and you'll dissipate energy there. And then evolves flow in the vertices and the plateau borders and even in the films. And those are all sources of dissipation. So there's definitely interesting viscous dissipation. Andrea and Sriram were the first, to my knowledge, to think deeply about how that happens in the linear response regimes of measuring G star, small amplitude oscillatory shears, and show that and presented a nice argument for why the dynamic shear modulus goes to square root of I omega. Dissipation in the films involved with sort of a range of orientations those can take with respect to the shear direction. So yeah, sorry. That if we were going down the jamming route, that would have been front and center, talking about dissipation.
Just one question. It comes from the last lecture. Generally, what I understood is the bigger the bubble is, and if there is a smaller bubble nearby, then there is a pressure difference between the bigger and the smaller one. And generally, the smaller one has higher pressure inside.
Yes.
So in that middle, the bigger bubble on the middle, the curvature is like this, where the bigger one, yeah, this one.
This one?
Yeah. So how come the curvature is towards the smaller one? Towards the northeast side, let's
well,
say.
we should count the number of 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a 9-sided bubble. This is a smaller sided bubble. So in fact, by von Neumann's law, this one will grow. So the curvature is right. So the rate of change of area is n minus 6. It's correlated roughly with size by size topology, but that's only statistically true. You very perceptively picked out a counterexample to the perfect size topology correlation. Here's a many-sided bubble that's smaller than a fewer-sided bubble. And that can happen. All right. I was going to say there's no decoration theorem in 3 dimensions due to plateau border curvature. Okay. So this relationship, this beautiful decoration theorem, is great for giving us a little bit of insight, but it's got some limitations. It won't get us very wet, and it won't help us in 3D.
I'm curious about, is there any self-similar structures, self-similar distribution, for example, for like the R's in Durian waveform?
Yes, indeed. So we will certainly, when we talk about coursing, I'm trying to think ahead to my slides, and I'm not sure if I show any plots that will convince you that there is a self-similar scaling state for wet foams, but but we have those data, and that's what we believe. So for sure. And that'll be important. That'll be important for later. So thank you. All right. So if there's no decoration theorem, what are we going to do in 3 dimensions? Well, there's, you turn to simulation, and there the workhorse is this surface evolver program that Ken Bracke has written and made freely available, and which Andy Kranick has used most notably to great effect in in looking at the structure foam. So here's a simulated picture of a wet foam. You can recognize the inflated plateau borders, and it's a nice random 3D structure. And you know, there you go. So there are simulation methods. Charlie Peskin has developed immersed boundary methods that are good also for for sort of flow problems, where these are good for sort of static problems. So there are some tools, but they're still hard. So I'm an experimentalist. I'm interested in this because they're important problems that you can't get at very easily with theories. So what can we do experimentally to get at the things we want to know? Well, you can look at the surface of bubbles, right? A surface of foams. You can do surface imaging, and you can also do multiple light scattering. Okay, so advance, please. Slide, please. So foams are white. So here's some nice, well, I guess the liquid's a little bit cloudy. No, yeah, the liquid's a little bit cloudy, but it's pretty clear. But the foams are totally opaque, and the reason why is because multiple light scattering. Photons reflect from interfaces, from gas-liquid interfaces. The photons will reflect. So the light does a random walk, and that makes it white, even if you have a perfectly clear sample. And this stymies you if you want to peer into the interior. Okay, you can't image the interior, but you can take advantage of multiple light scattering to develop probes of structure, namely the step size in the random walk is correlated with the average bubble size, so we can get the bubble size very easily. And if you do a dynamic version of this called diffusing wave spectroscopy, you can make contact with the bubble dynamics as they rearrange. Okay, so this is something that I've done a lot in my lab. Ranjini's done a lot with in the context of foams and actually other systems. And it's a good technique, but I don't think we're going to go down this road too much today. I just wanted to point it out. And it's cool, well, in the context of wet foams, it's also cool to think about how the light scattering properties, how the optics of foams vary with liquid fraction. Funny things happen, like the photons can channel inside plateau borders. So there's some cool transport physics there too. All right, so moving into then starting to segue into the coarsening stuff. Just to tell you that I've been interested in this coarsening process, both in itself and as a way of preparing samples for doing rheology in space. So I proposed this to NASA, like as soon as I got to UCLA, and I've been funded for an embarrassingly long period of time, literally to do foam experiments in space. Okay, so both coursing and rheology, and I've had a lot of fun along the way, working with jamming and thinking about comparing and contrasting the behavior of foams with other disordered solids, and so lots of good stuff here that we're not going to talk about today. What we discovered after sort of an engineering phase was that it's pretty difficult to automate rheology in space. So we descoped the project. Okay, this is obligatory to work on really just coarsening. And then we teamed up with a group of European scientists to bring the experiments home. Okay, so that's what I want to tell you about. That's what I want to lead up to.
Do you still do these microgravity experiments?
Sorry?
Do you still perform these microgravity experiments?
It's up there right now.
Can you send another one?
Probably not.
Okay. The reason
Yeah,
I ask is
it's
there
in
is
the
actually
so-called fluid science laboratory, and which is scheduled to be decommissioned.
because
they're gonna
there's
shove it out
now a
an airlock.
startup in Nevada that actually specializes in designing experiments to be sent up in space.
Sorry, what?
There's a startup in Nevada which specializes in designing and constructing experiments and automating them for remote control
Yeah,
that are to be sent up in space. They
that's
specialize
nice.
exclusively in that.
Yeah, nice.
So one wisecrack comment, no, two,
Okay,
if
two.
you will permit.
Okay,
One, do you know an instance where two rights make a wrong?
No.
Yeah, right. And second, you can literally call your stuff rocket science now.
Oh, thank you. Uh, the question is the difficulty of doing rheometry in space, and Mahesh said the keyword automated. So these are experiments that can't be done by astronauts. Astronaut time is too valuable. It has to be totally, fully automated, and it has to have multiple levels of containment. Even though it's just soapy water, we can't have soapy water spewing all over the International Space Station. It has to be multiple levels of containment. So those two requirements together, forget it. You just can't do it. Yeah. All right. So let's go, please. Slide, please. There we go. So here is foam in space. This is a space foam. Okay, this is a foam, a time-lapse movie of a 40% liquid foam. So it's actually below jamming. It's unjammed. Okay, it's kind of hard to tell that it's unjammed because the 40% the bubbles are still darn close to each other and they push each other around a lot. But this is an unjammed foam coursing in space. And the beauty of this is that there's no way you'd be able to measure something like this on Earth. It would drain like mad. The bubbles would rise, the liquid would fall. Doesn't happen here. Gravity's been eliminated for an extended period of time. Okay, this is like a 24-hour movie. Okay, so we want to understand how this works. No, so this is a T-tab foam. So it's a particular surfactant that's been shaken up literally. So there's just a closed sealed cell with a magnetic stir bar that's actuated to foam it up. I'll show you a picture of the apparatus a little later. So this is just to orient us a little bit. So there's the kind of thing, there's the kind of data we'd like to understand. This is from the so-called overview camera. We can see the surface bubbles. We'd like to measure their areas. Now their areas change with time. See how that goes. All right. So here's the model for doing that, the so-called border blocking model I referred to earlier. What we're going to do is suppose, and actually this is the brainchild of first Dennis Weir and Stefan Hutzler, and later these folks, though maybe they developed it about the same time and published later, I don't really know. But anyway, the idea is quite simply, we're going to suppose that something like the von Neumann law holds, the area grows linearly with time, or the radius grows like 10 to the 1/2, and the effective wetness is only to change the prefactor, and it does it through blocking gas transport. So if you like, there's gas transport through the film, the blue thing, but there's no gas transport through the plateau border. And as you make it wetter, this plateau border gets bigger and bigger, and therefore you block more and more liquid. Sorry, more and more gas flux. So that's the plateau, that's the border blocking model. And these two teams have different versions of what they think should be the effective blocking as a function of liquid fraction. This one just blithely goes to 0 at the jamming point, and this one is based on a sort of a calculation that's designed to be more correct in the dry limit. Okay, so this prefactor is supposedly going to account for, and this square here is going to account for behavior as a small perturbation from the dry limit. Okay, that's the idea, and that's why these two things are different. And so this is great. We got a prediction, and we can try to test that. So these guys tried to test it by doing experiments. Okay, Sriram, please.
What's the origin of these two functions? Is it based on an actual theory or just sort of playing with the?
Yeah, it's based on a picture of the microstructure, like
see.
this picture right here, and the fact that the radius of curvature, the thickness of the plateau borders goes like square of liquid fraction times the bubble radius.
Uh-huh.
It's based on that.
I see.
So that's a key ingredient.
Okay,
as
thanks.
is for these guys, Plateau's laws. Okay, so let's see if we can test that. So in my group, we have money from NASA, and right, to try to do as much as we can on ground, try to understand ultimately what to do with results from space. So we worked as hard as we could to measure coarsening as a function of liquid fraction. And we did that first for custom foams of uniform liquid fraction, so they would drain, but we tried to measure them before the drainage changed the liquid fraction in the region of which we're making measurements. Those are the solid symbols down here. We did it for foam samples that are simultaneously draining and coarsening, so actually they went to late stages, and we measured things as a function of height throughout the sample, okay? And we also did it for foams which were being bubbled. So we're sparging gas, we're blowing bubbles underneath, so there's a steady state column of foam, whereas getting progressively drier as you go up and the bubbles are changing their shape. It just comes to a steady state, so we can make measurements at leisure. So we made the measurements as best we could for the average rate of change of area of surface bubbles and plot that versus liquid fraction. And look, I mean, this is the best we could do. How good is it? It's pretty good. It's enough to say that the border blocking models, so these are the two functions I showed you on the previous slide, don't work so well. Of course, you know, they can't work at point J where it unjams because, you know, bubbles that are kissing are still going to coarsen. Even if they're far apart, they're going to coarsen. You cannot just totally block the gas flux. That's silly. Okay. Maybe it works here for dry foams. I don't know if it works here. And maybe this thing works okay. I don't know, right? So, so we did the best we could. It's pretty good. I'm proud of the experiments and the work my students did and postdocs, Kleber. But clearly we need to do better, especially close to unjamming. Okay, so let's step back from this approach of looking at 3D foams the best we can. And we're going to look at quasi two-dimensional foams squashed between plates where we vary the liquid fraction. And then we're going to return to the ISX experiments and wet foams in 3D. So let's start with the wet foams. So here's the movie I keep playing. And here's a picture of a poorly shaken foam in the same cell viewed from the side rather than straight above. So you can see that it's quasi two-dimensional. It's really bubbles squashed between plates. And here you can see how that works. There's a little blow up. So there's a window here, this clear window here is a film, and these things on the top and bottom are surface plateau borders that run along the surface of the sample cell, and then there's a vertical plateau border running between the gaps. Okay, you can see that there. You can't see that in this picture, but you can certainly see these little bright spots where light has been channeled through the vertical plateau borders between the cells. So that's kind of cool to look at optically. All right, so, and this cell, in fact, has a nice feature for allowing us to vary the liquid content. In other words, to vary the thickness of the plateau borders. The sample sits here, and it's surrounded by a circular trough in which we can control the amount of liquid. And this sets a gravitational pressure head, rho g times d, with which we can control the thickness of the plateau borders just by balancing the Laplace pressure, sigma, surface tension divided by radius with gravitational pressure at rho g d. So by changing d, by changing the filling height of this reservoir, We can control the plateau border thickness. As you can see, we can make the plateau borders thin and dry. We can fill this up and make it progressively wetter. And you can just see in these pictures, success. There, we're able to tune the plateau borders very, very finely as we go. And this, okay, it advanced, but I no longer have a pointer. So I'm afraid the battery is running out of juice. Let's see how we go. All right, so let's look at the geometry here a little bit. Does anybody else have a pointer? Or maybe some batteries? So on this slide, I wanted to find some geometry for us that will allow us to do the calculations. So we're going to call capital H the gap between the plates. That's an important geometrical scale that we control as experimentalists. The film thickness, L, we can't control. But now the radius of curvature, R, of the surface plateau borders, we can control. Thank you. Beautiful. Thank you. That works. Okay, we can control that then with the reservoir. So we're inflating the surface plateau borders. As we inflate those, the window closes shut or it opens up as we make this thinner. Okay, so we know everything about the geometry then. So that's good. So now we can calculate, we could do border blocking. We can also think about how much gas gets transported across not just the film, okay? The flux across the film is set by, per length in and out of the page is the height of the film, which is the gap minus twice the radius of curvature. So it's proportional to this geometrical factor and the stuff that sets the gas flux, physical chemical factors. So there's the geometry. We can do the same thing for the flux across the surface plateau borders. How much gas crosses this region here? Okay, so what we'll argue is that in the end, it will be set by this height here and an effective diffusive thickness of the plateau borders. E, average E. What is the average thickness of the plateau borders that controls the thickness? So we'll just write the flux this way. That defines the diffusive thickness. So this is a definition, if you will, of the average thickness. So what do we guess would be the average thickness, these plateau borders? Well, geometrically, you might guess as basically, what is the geometrical average thickness? It's just set by the plateau border thickness. Turns out that this is far too large. Okay, that's too large, then this is too small. There's actually much more gas transported across the plateau borders than you would think. And let me show you how to think about that, how it works. Okay, so what we're going to do is we're going to make what we call now a border crossing approximation. We're going to suppose we're just going to divide this up into little horizontal slices. We're going to stratify the concentration profile, and you can see it's kind of stratified. There's not, it's basically stratified here. So we're going to suppose that the flux decreases, if you will, linearly from here to here, according to the the thickness E. Okay, and the transport will be dominated by behavior here where the film is thinnest. So we'll just approximate it not by the actual circular shape, but by the leading term. So film thickness plus distance down from that height. So you measure y upwards from this point, and goes like that. So we can just plug this equation into here, do a little bit of calculus. And there we go. There's the expectation, the border crossing expectation for the average diffuse thickness. It's set by the geometrical average of the plateau border radius of curvature and the film thickness. So these two length scales both come into play in a non-trivial way. You can't ignore either, you have to use both. And this came as a surprise to us. Actually, the student who did this, actually, so there's Cody, there's the student. He's an undergraduate at Penn. If I can go back. These are his simulation results. He numerically solved the diffusion equation to get these gradients, and he calculated the flux, and he discovered that the flux is described by these two equations, but we didn't have a model for it, and then we came up with the model after the fact. Yes. It's a good question. So the way I drew it, this rate of curvature is the same as this rate of curvature, and we can make it different. We can make it different, and we have made it different. Okay, so I'm showing you the simplified version here where we're assuming they're the same, just for the simplicity of the story. And it doesn't change the scaling. You know, there's still the square root of the film thickness behavior that comes into play. That's a good question. All right, so there's the proof of the pudding, if you will, that Cody discovered that we now understand in terms of the border crossing physics. All right, so that's cool. We can now understand how that works, and we can take this understanding now to modify the von Neumann law. So we're going to include border crossing physics around this window frame. So film plus through the borders. We'll just repeat the von Neumann argument, including those two things, and here's what we find. So it looks like a mess. There's a bunch of terms here, but let's make it simple first. Note that the radius of curvature, right, the thickness of this frame goes to 0 in the dry limit, right? So here it's smaller, here it's wetter, so r is bigger. The dry limit, little r is 0. So let's set r to 0 and see what we get. So this term becomes 1, and here's an r. This term goes away. So in the dry limit, we have k0 times n minus 6. So you see, this is a perturbation away from the dry limit to the von Neumann law, including border crossing physics. So these are the new terms that account for what. So this term would be border blocking. If we ignore this one will close the window entirely when the radius of curvature is half the thickness of the gap. So it'll be totally blocking the gas flux. So this is border blocking physics. This one is border crossing physics. This one is also border crossing physics. And this one, in fact, represents a violation of von Neumann's law that's pretty dramatic. This one just changes the numerical prefactor, so it's not so interesting. But this one changes n minus 6. Okay? This one says actually that something else comes into play, and this is what we call a shape factor. It's a geometrical shape factor. It's a way it's something that quantifies the shapes of the bubbles. So square root of area, if you were to divide this by like perimeter, you'd get an ordinary something what people might call compactivity or elongation, something like that. You can normalize it to be 1 for a circle. But look at this. We're not going to divide by perimeter. We're going to divide it by the average curvature of all the bubbles. The arithmetic average curvature. Doesn't matter how long they are. We're just going to include each one the same. This is what comes out of the calculation. I didn't make this up. There's lots of dimensionless numbers you could pull out of your hat to describe shapes. This one came out of a calculation. So it's a funny and new kind of shape parameter that comes out of the von Neumann law. It says that for wet foams, shape matters, and here is how shape matters. Okay, so here's a little slide just showing what that shape parameter does. So it's normalized so that it's 1 if it's a circle. Without normalization, of course, it's 0 if there's no curvature at the end of the interfaces, and it becomes negative for large bubbles where the pressure is smaller than the neighbors. Okay, and here is shape distributions as a function of side number. And so there you go. There's some distributions that describe the shapes of foams. Very nice. So how about coarsening? Whoops. So here's the, if I can, there we go. So there's Anthony Kieko, who finished his PhD around 2021, stayed out for a postdoc for a little while, and he made some great measurements of exactly this effect. And here's a zoom in of one of his pictures with his analysis of the curvature of the plateau borders. So the green represents the average radius of curvature, and the red represents our uncertainty in the curvature. So we've got error bars on that, which is important as experimentalists. Got to know your uncertainties. Okay. And with that, we can check things out. So here is the dry limit that we talked about before. And here is the ADT, which should be constant if the foams are perfectly dry as a function of the shape parameter. And it should be linear in this quantity with a slope that depends on the wetness. And so the dashed lines are our expectations, and they're fit there to the data. You can see how they cant up. Okay, so we've got a pretty good description of what's going on there. So that's pretty good. So that's how things work on average. Let me show you another slide where it's a little more dramatic. So I think this is a better one to look at to show you that we think we understand what's going on with this. So here are areas versus time for 3 different 6-sided bubbles. Von Neumann says these should neither grow nor shrink, but look, these two shrank and this one grew and then started to shrink. So the behaviors of these 3 bubbles is really because this term is non-zero. Okay, and here is the circularity. So we measure the shapes. Measure the shapes, plug them into this equation, do the integral numerically, and that's the solid curves that seem to go through the data pretty well.
This might be a totally flaky question. Do issues like this matter for corrections of cells approaching confluence? I mean, not completely confluence is like wet. And so has anyone worried about that?
I don't think so.
You don't think they matter?
I'm not the person to give a definitive answer on that, but things like the vertex model, usually you give a penalty to changing areas and things like that, but you don't allow for exchange of area between neighboring cells.
Yeah, I guess the notion of stuff diffusing from one cell to the other doesn't really arise, and maybe that's the point.
Tissues. It works for foams, for emulsions, for grain growth, in alloys, and lots of contexts, but I don't think for tissues.
Maybe that's the point. Okay, right, thanks.
All right, so we're pretty happy with our understanding of the effect of wetness and border crossing physics from our 2-dimensional experiments, and let's see if we can bring that to bear in 3 dimensions. So there's 3 sets of experiments that are relevant in this regard. One is the ones I told you about already, where we basically, seems like border blocking is okay, up to jamming, up to unjamming. Okay, it seems kind of okay, but you know, the prefactor is kind of funky. If you remember back to that earlier slide, the data was a bit scattered, okay, and certainly something weird happened near unjamming. So, so those measurements. Georg Moret is a great experimentalist. He's done all kinds of important things, including developing multiple light scattering, dynamic light scattering, a technique called DWS. So he helped develop that. And he's done lots of cool things with colloids and neat things. Actually, he's doing things in neuroscience now. Anyway, he and his colleagues figured out a way to magnetically levitate foams so they can measure the coarsening behaviors. So, if you will, Georg beat me to the punch. You levitated some foams. So here is their data. Look at this. So here is the transmitted intensity. So this is from multiple light scattering. Remember I said the step size in the random walk is equal to bubble size. So they infer the bubble size from this. And it grows with time. and they fit those to pure power laws. And here you can see there's an exponent that's around 1/2. Here's an exponent that's around 1/3. Okay, so there we go. So I'll show you their exponents versus liquid fraction later. But for now, let me just remind you from the expectation from last time that the beta 1/2 is the limit of the dry foam coursing where border blocking works, right? So radius goes like time to the 1/2. So this is for bubbles that are jam-packed together. Beta 1/3 is what you get in the dilute limit, okay? And bubbles are very, very far apart. So, well, actually here I've got the slide to recap that. I guess I can just show that to you again. And basically the difference is because, well, in both cases, the volume rate of change is proportional to surface area times the diffusive flux. The diffusive flux is set by pressure differences and how that changes the gas concentration between neighboring bubbles, delta phi, and the separation, the distance across which the gas diffuses, which is the film thickness in the dry case, and a length scale given by the bubble size in the very dilute froth limit, where a bubble is separated very, very far from all its neighbors, and you're just solving the diffusion equation for a single sphere in an infinite sea of liquid. Okay, so this gives you 1/3, whereas this gives you 1/2. Okay, so those are the expectations again. All right, so said 3 sets of experiments. The third, here's a slide again, is the coursing experiments we did with our European colleagues on the International Space Station. And here's a picture of the apparatus schematically. So there's a little carousel, and in this carousel has different sample cells. So there's a bunch of sample cells here, and here's what the carousel looks like, and there's a sample cell, and this rotates into the measuring region. And it's sealed up with a known volume of liquid, so we know the liquid fraction once we make it. And there's a little magnetic stir bar in there that we can use to stir up the fluid. And it's a nice general purpose apparatus. We can do dynamic light scattering. We can do direct image to the surface bubbles. Okay, so lots of good diagnostics that are built into this. And it's a general purpose apparatus, which you can also use to study other forms of soft matter. And in fact, some of the folks on our RSI article are coming at this like this fellow is looking at emulsions with our apparatus, and this guy is looking at granular materials with the same apparatus. So it's a general purpose apparatus for looking at different forms of soft matter. We designed and built it so that that could be done, and we're going to use it to look at foams. And here's the movie I showed you earlier, and here's an example data of diameter versus time that you can extract both from such images as well as from multiple light scattering. So the light transmission works well to earlier ages. At very short times, the bubbles are too small to image very well, and at very late times, it's not thick enough to do really strong multiple light scattering, but the overview camera works, and you can see that the two data sets agree pretty well, and you can kind of splice them together and get a picture of what is diameter versus age. And there's some growth. And if we want to follow the Georg-Moret route, and actually some things I did earlier, we can try to think about fitting this thing to an effective power law. But if you look at it, it's not so power law-like, so that raises some issues. In fact, you got the same issues here for a whole sequence of liquid fractions that we looked at. So 15, 20, 25%, all the way 40% is the movie. I think this is the data I showed you on the previous slide, all the way up to 50% liquid in the samples. And there we go. So we're going to then think about how to analyze this data. Okay, so my interest is in the exponents, but I could say that, if I get this to go back, my colleagues, collaborators on the apparatus, whole thing, led by Dominique Langevin, their interest is more in the physical chemical prefactor. Okay, so they're interested in the rate assuming a certain exponent, and I'm trying to think about the exponent itself. So let me tell you my part of the story on that. So we're going to analyze that data by fitting it to effective power laws. And since the data on the previous slide didn't necessarily look power law-like, we got to ask, well, you know, is that because we didn't assume a scaling state distribution at time 0? So we're going to fit it both to a form that assumes a scaling state, as well as to a form that I argued last time represents a non-scaling state initial preparation. Okay, so we'll now treat these exponents as variable, and we'll do fits to these forms, both to diffuse transmission as well as to measures of the average bubble size that we get from the surface images. Okay, so there's a bunch of data and there's a bunch of fits. Okay, so we can get a bunch of exponents, and I myself went through this program for the data on the previous slide. Okay, and extract exponents. All right. So how does it look? Well, here's the story before the microgravity experiments came along. So I mentioned last time that I did this for a 8% liquid shaving foam and found an exponent that was certainly not a half. If you fit to a scaling form, right? It's more like 0.45 on average. Okay, it looks kind of like this point right here, Georg's data. And here's Georg's data, Georg and friends. So it's 1/2 in the dry limit, and it's 1/3 in the wet limit. But oh, wait a minute. What's going on there? Please advance. Ah, look at the crossover. It crossed over to 1/3 at the jamming point. Who ordered that? The 1/3 exponent should happen only in the very dilute limit. 1/2 for sure should be in the very dry limit. 1/3 should be only in the very, very dilute limit where the bubbles are far apart and you're solving a diffusion equation for a single sphere effectively in an infinite sea of liquid. That's where you should get the 1/3 limit. But Georg found 1/3 is attained much closer to jamming. So this is a big mystery. Why does this work? I have an explanation. Border blocking. Okay, so we're going to do the same trick as before. So here, Cody also measured, well, he simulated the gas concentration profile between nearly kissing spheres. So here, they're separated by a film thickness. Okay, and he measured the concentration of dissolved gas in between. Okay, and we can look at that and we can divide it up into little vertical segments and integrate it up and figure out what is the flux of material between those. And here's the equation we find. Rate of change of volume goes logarithmically in radius divided by film thickness. Okay, and you can solve this. You can't invert it, but you can't invert it for radius versus time, but here's time versus radius. Look at this, there's a logarithmic correction to beta equals 1/3. A logarithmic correction. So it's not pure power law, but experimentally you can't tell that it's not a pure power law with a 1/3 exponent, and it's because of border crossing physics. The film thickness plays a role. So it's not truly the dilute limit, not just because there's a logarithm there, but because the film thickness plays a role. So it's not the dilute limit, it's border crossing physics plays the role. And if you look at the data near jamming, there it is. And the two fits here is a pure scaling fit as well as the nearly kissing sphere fit to this form right here. That's the purple. And you can't tell the difference over the dynamic range of the data. Look, we're not going to do better. Look at the time scales here, right? So this is out to, you know, a day or two at most. You're not going to do better than this. You're not going to get another decade in radius. So there's no way to tell these two functional forms apart. with any reasonable kind of experiment that anybody can perform. We can't tell them apart, okay? But we do think it's non-power law, and we do think it's logarithmically faster than a pure power law with an exponent of 1/3. So that's pretty good. So that explains what's going on at the jamming limit. How about as we go above jamming? Well, I can do the same calculation for spheres that are pushed together. So here is a picture of surface evolver simulations from Andy Kranick of bubbles that are just above jamming. And you can see what they look like are spheres that are just faceted with little circular films. So how would you describe this? Well, you would describe it with, of course, the radius r, capital R of the bubbles. You would also describe it by the radius of the films, and we'll parameterize those by a dimensionless number f. So f times big R is the average radius of these facets, these circular facets. So this is going to be our model, and here it is pictured. And
Doug, so that means you assume that the facets have a size that scales with the bubble size.
correct.
Okay,
Correct. That's absolutely correct. So it's a bubble scale feature. And in the scaling limit, all bubble scale features should scale accordingly. So we think that's a good assumption. All right, so we know what the film thickness is, and we can repeat the calculation like I did on the previous page, and lo and behold, out comes two terms. One is this logarithm term that we saw before, which happens when f is 0, right? So take f to 0, and we get kissing spheres, so and this is the only term that survives, so that looks good. Then we get a term here that if we look at it, what is it? It's the area, well, it's the flux across the film. So there's a film contribution and a kissing sphere contribution. The first term gives us something that's logarithmically faster than time to the 1/3. The second term, if it acted alone, will give us time to the 1/2. So this interpolates, if you will, between a 1/3 and a 1/2 power law, depending on the prevalence of which term of these two terms, which term dominates. You get something that's closer to 1/3 power law, something that's closer to 1/2 power law, or something in between if both operate. So I don't think it's purely power law behavior. In fact, I can take this equation and I can integrate it versus time. If I go back a couple slides, that's this purple curve here, the circular facets fit. It goes to the data pretty darn well. That's a fit to that differential equation. It describes the data pretty darn well. Certainly as better as the sort of scaling fits. So again, I don't think the growth is pure power law. I'm sorry, I can't advance as I'd like. So it's not a pure power law, but I can extract, I can analyze this, I can use this to rationalize an effective coarsening exponent very easily. Please advance. What I'm going to do is take a weighted average of the exponents based on the size of these two terms. So beta is going to be 1/3 times this term plus 1/2 times this term normalized. So it's the weighted average of these two terms. This is going to be my effective exponent. And R bar here, right? R is a function of time. R bar means the average radius during the experiment, during the observation window. So the results will change with the observation window, but as an experimental fact, we're not going to change. We're not going to be able to make our observation window any bigger. So there's a pretty well-defined number there, and I can plug it in and make some predictions. And here it is. So here is Georg and collaborators' experiments and fit to my prediction. Here is the ISS data and fit to my prediction. And They cross over from 1/2 to 1/3, depending on what you think is this parameter f. Really, this is I like this because this is the only game in town. This is the only sort of new features I've introduced. The size of the circular facets. So it's a nice geometrical feature that you know has to be there. And you might think that it should vanish smoothly as you go to jamming. So I've got a couple parameters I can twiddle with. And I do that, and I get these fits. So in Georg's case, he has bubbles that we think are non-cohesive. So F0 is 0, and at the unjamming limit, there are no facets. This goes to 0 smoothly. So this goes all the way to 1/3. For the ISS experiments, the T-tab bubbles are slightly cohesive. They stick together. Okay? So even below jamming, they suck together and you have a non-zero interface. And that's what this parameter represents. So there you go. It goes to something non-zero. So this is cool also then because it gives us a way of getting at things about the microstructure that change as you change the physical chemistry of the system. Not all foams are alike. Physical chemistry does matter in the end. And we can get a handle on that through this. All right, and with that, I want to wrap it up. So there we go. Here's a summary of the effects of wetness on coarsening. So plateau borders play a big role. They have an effective, they have a geometrical size, and they also have an effective size in terms of coarsening properties. And we can use that to understand behavior in 2 as well as 3 dimensions with border crossing physics. And these are the most recent students who've been involved in this work. And with that, let me thank not just you, but for your attention, but a whole bunch of folks that have passed through my laboratory over the years, starting with Ranjini, including Menon, who was here, and a large number of other really great students and postdocs, and a whole mess also of great collaborators. So with that, let me thank you for your attention. I'd be glad to answer any more questions you might have.
Thank you, sir, for such an interesting talk. So, time for questions.
Yeah. You have mentioned something about how the contact numbers evolve with the volume fractions. As you go beyond the critical volume fraction, how your contact number evolves with power law, I think 1/2. But if you now at a particular concentration you apply shear, do you think that there is a evolution of the contact number or the same contact number arranged in different way? Because these are the soft things. So unlike the hard particles, because hard particle we know how the contact number evolves, but in such system where the deformability is plays the major role, do you think the under shear the contact number evolves or it remains the same?
I think it does not evolve. I think the contact number is independent of shear if you shear slowly enough. If you shear fast enough that the bubbles don't have time to snap into a new configuration, then you're in a situation where viscous dissipation matters. The bubbles are kind of whacked out of shape. Okay, they never lock into place. But if you shear slowly enough, the shear is essentially quasi-static and the bubbles are always locked into a jam position. And you're shearing them, you're just deforming the structure at fixed contact numbers.
Eventually it depends upon shear rate.
Eventually it depends on shear rate. High enough shear rates, for sure.
Thank you.
Come this far.
Logarithmic law for the r squared dr by dt. What is the origin of the logarithm there?
Yeah, so it's, I call it border crossing physics. It's really, this is going to take forever, I'm sorry. There we go. So literally the calculation is you divide this up into an annulus, circular annuli. And you think about the flux transmitted through that little region, okay? And do that calculation and this comes out. This is in 3D. Yeah, it's absolutely a 3D effect.
Radius of curvature near the contact, or the it's the okay.
In this case, capital R is the radius of the bubbles. So this is for nearly kissing spheres. So there is no plateau border. Okay, there's just spheres. So capital R is the radius of this spheres.
Okay, here in this case, the circular film, does it have a curvature, or it is just flat?
Oh yeah, good question. So if I advance a couple slides. So here is my cartoon for the case of two spheres in contact with a circular facet. And here's a simulation for that case. And you know what? The film is not flat. It can't be flat because there's a pressure difference between the bubbles. So it has to be curved. But it's curved on a scale that's small compared to the size of the bubbles. So assuming it's flat as I did here is not a bad approximation. But it is absolutely an approximation.
That's why it doesn't have any information about the curvature here, the
No,
equation.
no,
Okay.
no, 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 no. I'm not the person to worry about that. Andy's the person to worry about the actual shapes of these circular. They're not truly circular and they're not flat. They're complicated. But maybe not in a so interesting way. I don't think. Maybe I'm wrong.
This is not really an academic question, though. But I was just worrying about a comment made by Mahesh. No. That automating the experimental apparatus and everything. So a lot of PhD students are here. So is it going to take up the job of the PhD students?
To
Automation?
In the context of these experiments, we can't send graduate students to space any more than we can send more
So
astronauts.
one day those experiments are coming down.
They'll be shoved out in airlock.
The automation.
Yeah.
So most of the experiments will be automated, maybe.
And absolutely, if you're going to do experiments in space, it has to be automated.
I can add a remark to that. There is a virtue to automating experiments in the sense that human error can get diminished because of that. When there are multiple repetitive measurements involved. Second, life has sort of become easier, relatively speaking, with Arduino and Raspberry Pi. There's really an open source hardware movement now. So it used to be much more difficult when I was a student.
Yeah, automation is also great if you want to collect large amounts of data and apply the tools of data science and computer science and machine learning. You need huge data sets, and their automation is key. So yeah, there are benefits.
There is also a fledgling community that organizes a biannual series of meetings to look for ways of completely cutting out the human element and automating science using artificial intelligence. Let's just call them those who may not be named. So we'll call them Voldemort, because there are interests in my university as well as in India. So we will wish them well.
Are you allowed to ask questions?
It's actually not a question, it's a
I didn't
comment
think so.
following up on this automation thing, because several people in my group use ChatGPT for their coding, or I guess there's something on GitHub that they use for coding. And one of my postdocs says he thinks it speeds up his research by about a factor of 10. And he's very happy because it takes his time away from more routine things, and he can spend more time thinking about physics. So I think automation from that point of view is good, right? It allows students and postdocs to think more about physics.
So no more questions. Then we can thanks the speaker once again. And
Thank you all.